Good day, everyone. My name is Silas Quincy, and today I'll be presenting the design for the upgrade of Road D885 from a gravel surface to a standard two-lane two-way paved road. This project covers a section from Chenich 44.4 kilometers to Chenich 44.14 kilometers in Limpopo province. Over the next 15 minutes, I'll walk you through the design process, including the geometric layout, pavement structure, drainage design, and software-aided modeling. This is the resulting road corridor, as shown on my screen. The road D885 currently serves as a gravel connection between the surrounding villages and the proposed shopping center. The total length of the upgrade is approximately 3.74 kilometers, and the primary purpose of this project is to improve accessibility, provide a safer and a more reliable route for motorists, and accommodate the expected increase in traffic due to commercial development. And the motivation for this upgrade comes from the poor existing road conditions, frequent drainage issues, and the need to support the regional connectivity. And upgraded road will also serve the local commercial farms, such as a lime mine and over 20 surrounding townships, improving both economic and social outcomes. The existing road conditions, currently D885 is a gravel road with two lanes, each approximately 3.5 meters wide, and the surface is uneven and drainage is insufficient, leading to ponting in the flat section of the terrain. And the subgrade strength varies along the alignment as indicated by the CPR values obtained from the DCP tests. And these values range from 8% to 33%, reflecting areas of both weak and strong subgrade, as shown on the CBR values along the road table. The design standard and guidelines followed. So all the design work followed the South African Road Engineering Standard to ensure safety, constructability, and compliance. We referred to TRH4 for pavement design and TRH17 for geometric design of rural roads and TRH26 for road reserve and cross-section elements requirements. The material testing and classification were guided by the TMH1 and COLTO, while San Romano provided supplemental guidance for super elevation and drainage design. The traffic data and design inputs. As we know that traffic plays a key role in pavement selection, and the annual average daily equivalent AADE at the start of the design period is 375 E8S per lane per day, and the design period is 20 years with a pre-construction growth rate of 2% and the post-construction growth rate of 3.5%. Over this period, the cumulative traffic load is approximately 4.25 million E8S per lane, which classifies the road as ES10 according to TRH4 standard. The geometric design overview. The road is designed for a speed of 100 kilometers per hour, and horizontally the minimum curve radius is 400 meters, and the maximum super elevation is 8%. Vertically, crest and side curves are designed to satisfy the stopping side distance requirements, and the full alignment was developed in Autodesk Civil 3D, allowing us to model horizontal and vertical curves, cross-section, and pavement templates efficiently. The horizontal curve manual check as a key part of the design was to manually check horizontal curves for one representative curve, and the beginning chainage of the curve was 45.220 kilometers, and the end is 45639 kilometers. The proposed radius is 400 meters, which exceeded the minimum allowance radius of 379.47 meters. The applied super elevation of 8% was also sufficient, ensuring that the combination of friction and super elevation meets the specific requirements of the design spec. The pavement structure design was based on the TRH4 guidelines, considering the subgrade strength, traffic load, and local material availability. The selected alternative is the SO 30A cement treated base, and the pavement layers are as follows. The surfacing or wearing of 30 millimeters and cement treated base C3 of 150 millimeters and crushed base C4 of 300 millimeters, granular layer G7 of 150 millimeters, formation layer compacted G9 of 150 millimeters. And this is as shown on my screen. The drainage conceptual design. As we know that the effective drainage is critical to prevent pavement deterioration. Hence, for the road surfacing drainage is achieved using the side drains and crossflow of 2% to 4%. And the road reserve drainage include the meter drains and energy dissipators to safely convey water to natural water course. And the subsurface drainage was included because of moderate subgrade strength and seasonal saturation risk. The perforated longitudinal drains are installed in the shoulder areas to protect the pavement structure. Moving on to Civil 3D workflow. Civil 3D was used to model the corridor, allowing us to integrate the survey data, horizontal and vertical alignment, pavement layers, and the drainage features. The key steps included were that importing survey points, generating the TNI surface, designing horizontal and vertical alignments, creating the corridor with pavement templates, generating cross sections, and calculating the earthworks volumes. And this workflow, as shown on my screen, ensured accurate design and easy verification against the TRH17 and TRH26 standard. As a result, we have this earthwork summary. Earthworks were computed using the 3D, Civil 3D, and Master tools. Hence, the cut volume was approximately 38,706.24 cubic meters, and the fuel volume was approximately 4,851.67 cubic meters, which give us the net surplus of 33,854.56 cubic meters. The master strategy, we were going to reuse the cut material to fuel, hence minimizing the haul distances. The key takeaways: the upgraded D885 roads is going to improve on safety, access, and traffic flow, and the cement-treated base ensures the durability on the variable subgrade. The drainage design protects the pavement from moisture damage, and Civil 3D enabled accurate corridor modeling, earthwork planning, and the design ready for construction phase. The references for this design project was the TRH4, TRH17, TRH26, TMH1 photo specification and sunrow geometric design drainage manuals, and this DCPT test reports, as well as the survey data which was provided by the university. So this brings us to the end of the presentation. I thank you.